Okay. Hello, everyone. Welcome to the VR&D webinar on optimization technology and applications. Sorry about the technical glitch. My name is Fani Aduri. I am a support engineer here at VR&D, and I'll be host for this webinar. Today, I'm pleased to introduce our PEO, Dr. Gary Vanderplatz, who would be the speaker for this webinar. Gary founded VR&D in 1984, and he's a widely recognized expert in the field of optimization with about 4 decades of experience. He's also an AIAA fellow and the recipient of the 2002 AIAA Multidisciplinary Design Optimization Award for his application of optimization to engineering design. Today, he will speak about a brief overview of optimization theory and its applications. If you have any questions for Dr. Vanderplatz, please type them in the Q&A window in the WebEx panel. We'll try to get to the answers at the end of the presentation. With that, I would request Dr. Vanderplatz to talk about optimization technology and applications. Gary,
okay, thank you, Fanny. And thank you for all attending. Sorry for the little glitch. I'm in Arizona. Fanny's at home with a cold, and a lot of you are all over the world, many of you losing sleep to join this, so I appreciate that. When I started in optimization, got my degree in 1971, in those days, we wrote our own finite element code, we wrote our own optimizer, and we presumably did some good research and published it and got a degree. Since then, we've had about 4.5 decades of research and development. In the late 70s, I began giving short courses in optimization, which would be 1 week long. Since then, we've had another 30 years or so of research and development. And now today we're going to cover all of that in 1 hour or less. So this will go very fast, and I apologize for that. That's the nature of things, but the information is on our web, and you can download it and study it in detail. And feel free to contact me at any time with questions. Well, the first question is, what is optimization? It's just a very general automated design technique. And the beauty of it is its generality. We can optimize anything we can analyze and even do experiments on. Well, what does it do? It changes important parameters to find the best design subject to our specified criteria. And I say best, I don't guarantee an optimum. We're engineers, we want to get an improved design. I've had people call me and say, your optimizer doesn't get the optimum. It should be 6.000 and you get 6.001. And I argue that that's a lot of the motivation of my own work in optimization, is that it's an engineering tool and we want to get a very good design very fast. In that light, design of experiments is not optimization, parametric studies are not optimization, and univariate search is not optimization. Optimization will change all of the design parameters simultaneously and consider your objective or multiple objectives and constraints all at once, limits. Why should we use optimization? It'll reduce design time, improve quality, and it frees the engineer to have the creative thinking that we all knew God intended for us to spend our time on. It's interesting that I've used this slide for many years, and to be honest, until about 5 years ago, I never saw design time reduced. Because engineers, if you're given 6 months to design something, you will take 6 months. In the last few years, management has figured out that optimization can, in fact, reduce design time, and so they've shortened the design cycle, and people use optimization to make that happen. So what does it do? Imagine you're a little boy standing on a hill with a blindfold on, and you want to find the highest point on the hill inside of the fences. The rule is to get to that point. In this case, you want to stay inside the fences. Now, in practice, you may start outside the fences, and we have techniques to get you back inside. But imagine how you might move up the hill. To begin with, the hill is our objective function. We want to maximize the elevation on the hill. The fences we call constraints, and by convention, we'll say if that function defining the fence boundary is negative, we're inside. If it's positive, we're outside. So the optimization problem is we're going to maximize the objective. In practice, we minimize, but if you want to maximize, you just minimize the negative of the function. Subject to constraints, and the longitude and latitude are the design variables. So how do we do this? You might imagine that you take a little step in the east-west direction, a little step in the north-south direction, and from that you can sense the slope of the hill. What you've just done is calculate a steepest ascent direction by finite difference. Okay, now let's move in that direction, and we'll move in a straight line as far as we can until we either cross the crown of the hill or we encounter a fence. In this case, we hit the fence. We call that the one-dimensional search, and you count the steps to hit the fence. You can take partial steps. Once we hit the fence, we repeat the process. Take a little east-west step, a little north-south step, and from that we determine the slope of the hill, and we determine the normal to the fence, which is its gradient. In other words, we've calculated the gradient of the objective function and the constraint. Now, because we don't know the nature of the fence, in this case it's curved, we'll find a search direction that pushes us away from the fence, which is a feasible search direction, and which increases our elevation on the hill, which we call a usable direction. And we repeat the process. In this case, we hit fence number 2. If we knew in advance that fence number 2 is straight, in other words, it's a linear function, we can actually go tangent to it. If we didn't know it was straight, we would zigzag our way up the hill. Okay, so this is basically defines a method called Zoutendijk's method of feasible directions, which he wrote a book in 1960. It was so hard to read, it was out of publication by 1965, but the physics are very accurate, and his concept of a usable, feasible direction is fundamental to much of what we do in optimization today. So the optimization problem now says minimize a function called the objective function with limits on other functions which we'll call constraints. The key to optimization is the vector x that contains the design variables can have many design variables. We have solved problems in our Genesis software with over 2.4 million design variables. You can have many constraints, and it's not uncommon to have millions of constraints in structural optimization. And the key is that we consider all of these functions simultaneously. If you look at problem size, my mentor Lucian Schmidt published a famous paper called Structural Optimization by Systematic Synthesis in 1960. And he solved a 2-variable 3-bar truss problem. And years later, he wrote a paper saying it took half an hour on an IBM 650 computer, and you had to be a congenial optimist to believe in optimization with runtimes like that. Well, today, with our Big Dot software, I've solved a test case with 500,000 variables and 500,000 critical constraints. And in topology optimization, as I said, we've done 2.4 million variable problems. If you look at learning optimization today, you don't have to be an optimization guru. A computer literate engineer can learn to use a program like VisualDoc in a day, become pretty capable in a week, and quite advanced in a month. Well, does it work? My first job was at NASA doing conceptual aircraft design, and this is an example of a supersonic, it was called a supersonic cruise vehicle. Eventually it became the F-22. This is a multidiscipline design optimization problem. We had about 5 disciplines: structures, aerodynamics, propulsion, and so on. And we would do trade-off studies. And the key constraint would be the sustained load factor. We wanted to minimize the mass of the aircraft. And as you increase the required load factor with conventional technology, you couldn't go beyond about 6 Gs until the aircraft just grew too much. So if you used advanced technology, and this is a conceptual design program, so it's very simple semi-analytic equations that we use. If we had a 20% technology improvement, we could in fact grow the aircraft and get the 8Gs requirement. In '76, my boss came in and says, hey, here's a paper published by a PhD student. He's got the idea that if you take a high-performance aircraft on a ship, if you put a ski jump out there at the end, by the time you get back to the water, you have flight speed. Well, the difficulty with that was the ski jump had about a 20G load on the landing gear, and when you got back to the water, you were going down at about a 20-degree angle. That was a variational calculus study, and when we did optimization, we could say we don't want more than a 2G load, and when we get back to the water, we want a 500 feet per minimum climb rate. Now, that's not to criticize the variational calculus. The guy got a PhD, so he achieved a lot. And he also created the idea that now is used in the fleets. They don't have 20-degree ramps. They have 2 or 3-degree ramps. But the point is that with optimization in 2 hours, we were able to get a realistic ramp design. In '76, I got involved in aerodynamic optimization. I wasn't confused by any knowledge of the subject, so I was able to try ideas that other people wouldn't do. And so I did curve fits. Today we call that response surface optimization. Here's an example of maximizing lift with drag and moment constraints, or minimize drag with lift and moment constraints. Well, these examples are now about 40 years old. The aircraft example was a one-person-month study verified by a 1-year, $250,000 study by a commercial aircraft company. The takeoff example, as I said, was solved as a PhD problem that got the wrong answer. The airfoil example produced a design almost identical to what was called the GAW2 airfoil from Dr. Whitcomb at NASA Langley. So it's not debatable that optimization is useful. It's been working for a long time. I think the difference is today we have software that you can learn to use, as I noted, very, very quickly, and we can also solve problems that are orders of magnitude larger than we could solve in the 1970s. Well, some definitions. I'll talk about design variables. Those are the parameters we change to improve the design. Some people call those decision variables. Objective function is what we want to minimize or maximize. Some call that the merit function. Inequality constraints are the one-sided conditions like stay inside the hill. Equality constraints are precise. Now I'll talk mainly about inequality. You can just imagine if you have an equality or required the function equals 0, just make 2 equal and opposite inequality constraints. And side constraints are bounds on the design variables. In other words, if you're designing a table, you don't want the thickness to have a negative value. So the lower bound might be a millimeter or 2. A feasible design satisfies all constraints, that is, you're inside the fences. Infeasible design violates one or more. It's very common in engineering that we start infeasible. And so basic concept that's always been part of our work in optimization algorithms is that if you have a constraint violation, the first task of the optimizer is to get it into the feasible region and then improve it to an optimum. And we call an optimum one that satisfies the minimum or maximum objective and satisfies all constraints. There's what's called the Kuhn-Tucker conditions. There are mathematical ways to prove that we have an optimum, or at least a relative optimum. There may be numerous optimum. We don't know because we can't see in 100 dimensions. And we'll use a 2-variable function space just to describe some of the technology. So finally, the optimization task is minimize f of x, subject to g of x less than or equal to 0, and x between lower and upper bounds. Consider a simple example of a cantilever beam. We want to design the width and height. We have stress constraints. We have a deflection constraint. We have a height over width constraint. You can think of that as a buckling constraint. And we have bounds on the design variables. We can now plot the 2-variable function space. And here's the upper bound on the design. These are contours of the objective function. decreasing to the left. Here's the boundary on deflection. Here's the boundary on stress. And being a good civil engineer, you might think, well, the stress and deflection constraint are going to be critical. I can create two equations and two unknowns and find this point right here. But that's not the optimum. The optimum, in fact, is down here. Optimization has the advantage that it doesn't have any preconceived notion of what the solution should look like, so it can find an answer that we may not anticipate. So optimization now is a two-step process, and there are many different methods. In the 1950s, random methods were very common. In the 90s, genetic algorithms, which are a random method, became popular again, and they're still popular today. I've always focused on gradient-based methods just for efficiency. And it's a two-step. First, we find a search direction, that is, take little steps north and south, east and west on the hill, and then we search in that direction and go as far as we can before we have to find a new direction. So let's assume, we'll start by talking about the one-dimensional search. Assume we have a search direction that will improve the design. We now want to minimize f of x plus alpha s, where alpha is the step size and a function of one variable. You can think of this as the design plus a perturbation, which is exactly what engineers do all the time. And then g of x plus alpha s has to be less than or equal to 0, and if you include equality constraints, you have the same for them. And the design has to stay within the bounds. There are two methods. One that we use a lot is polynomial search. Another is golden section. If the design is infeasible, we search for a feasible region if possible with a minimum increase in the objective. If we can't find a feasible solution, we want to find a point where the constraint violations are minimized. Several possible cases. Initially feasible with no active constraints. That was like the little boy on the hill. Initial feasible with one or more active constraints. Perhaps infeasible, we have a violated constraint. And we may be infeasible and not be able to find a feasible solution. Now, a detailed discussion of this is probably about a 5-hour lecture, so I just want to give you the flavor of what we have here. We approximate the objective and all constraints as polynomials. For the objective, we look for alpha that will minimize f of x plus alpha s, or f of alpha. For constraints, we look for where the constraint bounds are. From all of those, we choose the one that improves the design the most. Polynomial interpretation is good for finding the minimum or zero of a function of one variable. It takes relatively few function evaluations. It should be limited to cubic interpolation. If you get more, it takes more points to get to the optimum. We simply use the nearest 3 we have, or 4. It's better to interpolate than extrapolate, and there's no guarantee of accuracy. However, if function evaluations are very expensive, that is, when we calculate the elevation on the hill or the distance to the fence, then this tends to be the method of choice. An alternative method is called golden section. It's not quite as efficient as what's known as Fibonacci search, but it's easier to code, and it's actually works better for a lot of, it takes one fewer function evaluation. The idea here is we first get lower and upper bounds, and then we get two interior points, alpha 1 and alpha 2. Alpha 1 is 38% from the lower bound. Alpha 2 is 62% from the lower bound, or 38% from the upper bound. Here, in this case, the function f1 is larger than f2, so this becomes our new lower bound. And by doing things the way we just did, it turns out that alpha 2 is now 38% of the distance between the new lower bound and the new upper bound. One more function value at 38% from the upper bound is alpha 3. This is now a new upper bound, and the process repeats. The golden section ratio, as it's known, is 1.618. There's some fairly simple mathematics that drives you to that. If you look at Da Vinci's human body, this is our only homework assignment. A over B, the distance from your navel to your top of your head divided by your height, should be 0.38. So you can check that as a homework assignment. It's good for finding the minimum or zero of a function. If you want the zero, you minimize the absolute value. That's the only one of the few times in optimization we want to minimize absolute values because it's a discontinuous derivative at zero. You might use it to reduce the tolerance before using polynomial interpolation, and that's our method of choice in our dot and big dot optimizers. It takes a lot of function evaluations, but you can guarantee the accuracy to whatever precision you want. So if function values are cheap, this is the method to use. The dot optimizer and also the big dot optimizer starts with golden sections and switches to polynomial. Well, how do we get that initial step size? If you take too big a step, the polynomial fit will be poor. If it's too small, it'll take a lot of steps to bracket the minimum. So we have a lot of internal decisions to make in the optimizer to try to pick a good step size. We always use as much information as possible, and as we get more information, we increase the polynomial order up to a cubic. So to summarize, we're going to find the single parameter alpha that will minimize f of x plus alpha s, and that we're going to update the design by moving that distance. It turns out that the actual implementation of the one-dimensional search is probably the most difficult part of coding an optimization algorithm. When I wrote the Conman program in 1972, which is sold by many of our competitors today, the original one-dimensional search routine was about 60 lines long. Today, by the time it was evolved over 10 years, the one-dimensional search was about 600 lines long with 60 if tests. And I can't even describe what it does anymore. So now let's look at getting the search direction. Sequential linear programming. When I was doing my PhD, Professor Schmidt would send us to the operations research department for theoretical study. And I was taught that SLP is a terrible method to use. And then when I wrote my textbook, I coded it to show how bad it was. Turns out to be pretty good. Basically, we linearize the objective and constraints. We then use what's called the simplex algorithm to minimize that. For that cantilevered beam, if you start here and linearize it with these black lines, the approximate optimum moves to here. And so you can see you make very good progress very fast. It's very good if you end up with a fully constrained solution. So if you have a particular optimization problem or group of problems, class of problems, if they tend to end up with as many active constraints as you have design variables, SLP is a good method. The method of feasible direction, as I said, was developed by Zotendijk in 1960. That's contained in the Conman and ADS programs. Conman was 1972, ADS was 1984. These were research codes when I was at NASA and the university. It finds a near optimum very fast. The little boy on the hill basically describes this method. I'm not going to go details here for lack of time, but basically we end up solving a we look for the components of S and the value of this parameter beta that we're going to maximize in a linearized fashion. The difficulty is that we have a quadratic constraint here. It turns out that most textbooks convert this to a linear constraint where we say the components of S are between plus and minus 1. We actually deal with it properly and it's described in Zotendijk's book, but it's very hard to understand. Once you understand it, it works. We push away from the fence depending on how far we are from the fence. That's a quadratic function. And so the philosophy here has always been try to mimic the mind of a good engineer. And what a good engineer does is if he knows he's getting near the constraint bound, say his design is, if he's doing structural design and he calculates a stress of 15,000 psi with a bound of 20, he starts to worry about it and he'll start to push away from it. And by using this quadratic theta, when you hit the constraint, you push harder than when you get near it, you push just a little bit. If you get outside the constraint, you push very hard. And that has this effect. If you have a very large theta, you'll find a search direction that doesn't change the objective function much. If theta is 1, it kind of bisects the angle between the objective and the constraints. If theta is 0, it will follow the constraint. And we have the gradient here of the objective and the constraint. And the search process looks a little bit like this. The modified method of feasible directions, which is contained in the dot optimizer, is very similar, except we always use a 0 push-off factor. If you're into optimization theory, everybody that studies the method ends up with their own algorithm, and I published this in the mid-1980s. It's the same direction finding process, but we don't have a push-off factor theta. If we have violated constraints, we'll have the push-off factor. What it does is, if you have no active constraints, you go in the steepest descent direction, or what's called a conjugate direction if you take more than one iteration to hit a constraint. If you have an active constraint, you'll find a search direction tangent to it, but you can see you may go infeasible right away. If you have a violated constraint, you'll find a search direction pushing you back to the feasible region. Once you have the search direction, we now have a technique to follow this curve constraint. This method is similar to the generalized reduced gradient method, except that method separates this into independent and dependent variables. I found a way to find a move back to the constraint boundary by minimizing this distance, and that's contained in the dot optimizer. And here, this method will hit a constraint. It will follow that constraint to the intersection with another constraint and follow that constraint to the optimum. Like the feasible direction method, it gets a near optimum fast. It deals with equality constraints by treating two equal and opposite inequalities. Does better than the method of feasible direction because we're constantly using the Newton-Raphson step to bring us back to the boundaries. And that's used in our dot optimizer. The third algorithm in dot is called sequential quadratic approximation. That's a pretty complex method that basically is hard to really draw a picture of, but it creates a quadratic approximation to the Lagrangian function, which is a bit beyond this discussion. But it's an important method, and if it works well for your class of problems, it tends to be the best of the three methods. But it's very sensitive. When I first programmed it, Professor Yoshida was visiting me from Japan for a year. We published a paper, and then shortly after that, Jaz Aurora from U of Iowa published a paper. And we both said we had to modify it to make it work for engineering problems. And we both modified it pretty much the same way. It's got a strong theoretical basis. Theoreticians like it. If you don't have a feasible design, you have to put in a lot of modifications. Well, how do we know when we've reached an optimum? Well, we always have a max iteration counter because if you have an iterative method, sooner or later it will iterate forever. If you satisfy the Kuhn-Tucker conditions, that is, we cannot find a search direction to improve the design, we can detect that and stop. Or we have diminishing returns, the absolute change in the objective function or the relative change. And if we go enough iterations without getting a feasible solution, we can demonstrate that none exists. But what we try to end up with is telling the user which constraints are preventing us from getting a feasible solution, and you need to modify those constraints or change the design somehow. Now let's look at the same cantilevered beam with 10 variables, height and width of 5 segments. We'll look at SLP, modified feasible directions, and SQP. They all get about the same design. They all take about the same number of iterations and the same number of function values. Don't look at this too close and say, well, SQP is always most efficient. If you change the problem just a little bit, you may find that one of the others is more efficient. But this is typically, this is 10 variables. When people ask me how many function evaluations it takes to do optimization, I usually quote 10 times the number of design variables plus 40 or 50, and that's about what we have here. Now, penalty function methods were very popular in the 1960s. In fact, Fialko and McCormick actually wrote a book on them. Here, the idea is we create a pseudo-objective function, which is the original plus some penalty parameter. There are exterior, interior, extended interior. When I was writing the big dot optimizer, I looked at 13 different penalty function methods. But we'll talk about mainly the exterior, which the theoreticians don't like and I love. The reason I love it is if you violate a constraint, you create a penalty to push you back to the feasible region. But you only have to worry about violated constraints. So if you have a 1,000 variable problem with 10 million constraints, you only have to worry about those that become violated, or active, I should say. If you look at DOT, the difficulties as the problem size grows is the exponential growth in memory and the exponential growth in CPU time to find the search direction. The big dot program creates an exterior penalty that if you have the objective function plus a big constant multiplier times the summation of the constraints, and you only have 0 or g. So if g is negative, that is, it's feasible, you don't even have to worry about that constraint. This R sub p, j super p, looks a lot like the Lagrange multiplier, and if you use the augmented Lagrange multiplier method, this would be the same. I wasn't able to make that work on really large problems. So we actually have a proprietary method for calculating these little r's that we don't publish because they work like magic. We need the gradient. That's just the summation of gradients, and so it takes very little memory to store that information. In fact, if you only have enough memory to get 1 or 2 gradients at a time, you get that gradient, you add it to del phi, and so on. Handles equality constraints and redundant constraints without loss of generality or inefficiency. Other methods, like the modified method of feasible direction, can generate singular matrices that you have to deal with. That problem is eliminated here. We use a method called Fletcher-Rees for the subproblem that requires virtually no memory. Direction finding process is very simple and very fast. And that's what's contained in the big dot optimizer. And with that program, as I said, I've solved 500,000 design variable problem with 500,000 active constraints. We don't see today a particular limit on the size of problems we can solve. And to our knowledge, nobody else can solve problems of that magnitude. If you look at the memory requirements, modified method of feasible directions, if you have 5,000 variables and 5,000 active constraints, you can see you have 10 to the 8th, 10 to the 9 words of memory required. Big dot can use as little as 160,000, although it can use 10 to the 8th if you have that memory available. Also, we handle discrete variables. There's no good theoretical way to deal with discrete variables for large-scale problems. This method's contained in big dot. We have another proprietary optimizer called discrete dot, which tends to be a little bit better than this. But the point being that we can deal with discrete variables like the number of plies in a composite structure. Cantilevered beam again. Now this problem, we can make it as large as we want just by adding the elements to it. And so with big dot, as I said, I've done 500,000 variables. What's key here is this is the number of function values, and this is the number of gradients. And you can see this is for small problems, it still takes a lot of function values, where here 50,000 I consider small. But the efficiency is about the same no matter what the size of the problem. I can't theoretically explain it, but I like it very much. An aircraft wing solved with our Genesis code. This is a small model, 50,000 degree of freedom. Today we work with 10 million degrees of freedom routinely. 1,250 design variables, 84,000 constraints. If you have, say, 1,000 active constraints, dot gets a good enough answer, but it takes 2,870 CPU seconds total, of which 2,600 is in the optimizer. Big dot use almost no time in the optimizer. So it takes very little memory. It's a very straightforward method. There's some tricks in there that we don't tell people about that make it very fast and very reliable. Well, this is black box optimization. It's useful probably for 90% of everyday design tasks. We provide this in our Visual Doc software that has not just these methods, but if you like the random methods, we have that available. We have design of experiments available. We have response surface optimization available, on and on and on. It's a very sophisticated software that allows you to couple optimization with just about any analysis you have. So it's useful for just about all of our everyday tasks. You don't need a lot of special knowledge. You have to formulate the problem, because if you forget a constraint, it will be violated. But I submit that it's the most powerful design assistance tool we have available. Here's an example of turbo machinery, just to give you a flavor of how complex the outline of the process can be. This is in Visual Doc, and we actually use Genesis, I think, in here too. I'm not sure, but the optimizer is Visual Doc. Aerodynamic design of a windmill. This is a client in Japan, so we can't give you any details except to say that they reduced the drag coefficient by 14% with very limited changes in the shape of the vehicle. It's interesting, if you do something like this, optimization does a good job of making a very aesthetic design. Optimization will model nature rather nicely. Well, what about structural optimization? We have to worry about topology, geometry changes, gauge sizing, like this cross-section of bars or thickness of a shell. Imagine we have supports and we have a load. We have to find the structure that goes there. We have strength, stiffness, dynamics, and a multitude of other responses in structural optimization. Finite element analysis is extremely well refined today, so we can do the analysis of very, very large problems. We can do sensitivity analysis. It's interesting that one of my professors, when he was doing his PhD, he said, I need du by dx, and since it's an implicit function in the finite element equations, we have to do that by finite difference. The operations research professor, Leon Lasden, was on the committee, and he raised his hand. He says, why don't you just differentiate it? You have k du dx equal dp dx minus dk dx times u. And this part here is very easy to calculate. We've already decomposed k, and so we can get du by dx very simply. dp by dx is 0 except for body forces, thermal loads, and so on. dk dx by dx is very sparse, so we don't actually build that matrix. We just do the matrix vector multiplication as we build it, and so it's relatively easy to calculate this. These are available for a very wide range of responses. In some cases, we can't do it. We can't calculate the sensitivity of the element stiffness matrix analytically. In those cases, we use what's called semi-analytic sensitivities. That term was created by the people at General Motors Research Labs in about 1980. So history here is 1960. Schmidt did his classic paper. In the 60s, we could solve a lot of small problems, but nothing practical. Schmidt and his student Farshi, and later his postdoc Mura, developed approximation concepts in the 70s, and in 85, myself and others developed second-generation methods. Before 1974, we had a control program and an optimizer. That called the analysis, and that called the sensitivity analysis. Today, we call the finite element analysis. We can screen constraints to ignore those that are not critical or near critical. We do a sensitivity analysis on what's left, and we send that to an approximate problem. And that is what goes to the optimizer. So the optimizer itself did not get any more efficient over the years. It's gotten more reliable. We can solve much larger problems, but we still take, a few hundred analyses maybe. The beauty is that the approximate problem is so fast, that's acceptable. Why do we need approximations? Because there's too many variables, too many constraints, too many detailed analyses. Well, today we don't worry about too many variables. We can solve the million variable problem. For constraints, we delete those that aren't critical or near critical. And then the big expense is the detailed finite element analysis. We want to get an optimum with about 10 to 20 finite element analyses, even though the finite element model may have 10 million degrees of freedom and we may be doing very complex analysis. Design variable linking is a simple concept that says if we have a plate with a hole in the middle and we want to move the boundary, if you only move the boundary, you very quickly destroy the mesh. On the other hand, if you link the variable so that if this node moves inward 1 centimeter, this one moves inward 0.5 centimeter, then you maintain a good quality finite element model as you progress. So the design is the linear combination of other designs. And that's exactly the technique that I used in the 70s on airfoil optimization. When we first started doing that with people named Hicks and Merman, we modeled airfoils with quadratic or polynomials. That didn't work very well, and so I said, why don't you just go get airfoils out of the NACA book and pick the best combination of those, and that works like a charm. Constraint deletion, a lot of constraints are far from critical. Gradient computations can be costly, and good designers ignore non-critical constraints anyway. So again, we're modeling the mind of a good designer. One way is to say any constraint that is more negative than -0.3, we can ignore for this cycle. Now, this is for one step in the optimization process. Later, if some of these become critical, we'll add them back in. Also, since we have very refined finite element models, a lot of these constraints might be elements that are very close to each other. So all we have to do is just keep a few representative elements and delete those others. So here in this region, even though a lot of constraints are near active, we may only retain a couple of the two most critical. So the key idea is we do a detailed analysis, evaluate constraints and delete those that are not critical or near critical, get the gradients of what's left, create a high quality approximation, use that to optimize, and repeat that. That's one cycle in the process. What are intermediate variables? Imagine now the cantilevered beam and we want to calculate the gradient of the deflection. If the design variable is the height, the gradient, if we do a linear approximation, we find that's u0 minus 12 pl cubed over ebh to the fourth. We made a very nice, it's very highly nonlinear. On the other hand, if we let the design variable be 1 over the moment of inertia, it's exact. Now it's exact because this is a statically determinate structure, but in general it's a good approximation. And so now instead of designing the dimensions B and H, we design the section properties. Now we actually design B and H, but we approximate, I should say, in terms of the section properties. So the design variables can be the physical dimensions. The intermediate variables can be highly nonlinear functions of those variables, but we capture a lot of nonlinearity. Responses are more nearly linear in the intermediate variables. And in the 70s, actually an intern worked at the company for a whole summer trying to design A and I and then fit the B and H and the T to it. This avoids that. So what about intermediate responses? The original concept, Schmidt and Farshchi in the 1970s, said if you consider a simple rod, stress is proportional to force over area. Area is the design variable. So let the design variable instead be 1 over the area. Now sigma is F times X. We linearize that, and for a statically determinate structure, this is exact. For a indeterminate structure, it's a very good approximation. Worked very well for rods and membranes, did not work for plates and shells and beams and so on. So in '85, my students and I published the idea of approximating, instead of the area, the stress, approximate the force. Now, I get credit for this, but I have to say this was Professor Bofeng in China published the idea a few years earlier. Unfortunately, published in Chinese, so most of us didn't know about it. But if we approximate force, that's now linear, it's explicit. When we need stress, we approximate it by dividing by the area. So now the design variable remains the area, and you can show that this is actually a one order higher approximation. I had a student named Scott Hansen, who today is a very well-known lawyer in Los Angeles area, but at that time he came to work for me. He was doing a master's degree, and I told him, you know, work on the force approximation. In about a week, he'd solved all the reasonable problems, and he was getting answers to my PhD thesis examples 10 times faster than I was. And he said, there must be something more to work on. And I said, well, try doing shape configuration optimization of the truss as well. Well, imagine now we have a simple beam rod against the wall with the load. The design variables are the area and the horizontal location of the support X. If you approximate the stress, you can see that the X's and A's are all over the place. It's very highly nonlinear. If you approximate the force, it's still nonlinear. We have X down here, but it's, if you look at this, the X's kind of cancel. And well, it's nonlinear, it's much less nonlinear, and it's uncoupled. The area is no longer here. Again, it's statically determinate. This made a dramatic improvement for configuration optimization in addition to sizing and shape. So we have different approximations for different responses, and we spend a great deal of time refining these approximations in our Genesis code. For eigenvalues, Bob Canfield, I believe it was 1978, said if you take the Rayleigh quotient, approximate the numerator and denominator independently, and you get a much better approximation. That leads us to a very simple concept. Consider a simple function 1 plus x over 1 minus x. Highly nonlinear, it's undefined at x equals 0. But if we approximate the numerator and denominator independently, of course, because they're both linear, it's exact. The point being that if we look closely at our problem, very often simple changes in problem formulation yield very good results. And that's kind of a lecture all itself. I learned doing conceptual aircraft design that instead of letting wing loading be a design variable as designers usually do, if the wing area is a design variable, the optimization task becomes 10 times easier. So the idea is we use intermediate variables in response for stresses, strains, dynamic response, just about any response imaginable. The key idea is to create a high quality approximation based on physics. What's the cost? We want to get a good optimum quickly. We want to use as few finite element analyses as possible because they are expensive. And typically we get an optimum with about 10 to 20 times the cost of one analysis. We create unique approximations depending on the design variables and responses. We fine-tune everything. And here you've seen just a small piece of what we have. In our Genesis code, we have topology optimization, we have sizing optimization, shape optimization, topometry, where we let every element have its own design variable, topography, where we can automatically design bead dimensions. It's basically a shape optimization. Freeform is another form of shape optimization that allows us to generate ribs. You can imagine if you try to set up this problem by hand and you open a finite element input file, you could spend the rest of your life just defining the design variables when you have a million of them. We take care of all of that in our Design Studio software that allows you to set up the optimization task extremely fast. And we do composite optimization. A good example of composite optimization, what the Formula One people do, they've designed the front wing on a Formula One vehicle so that it'll actually droop a little bit under load and they get a little bit more speed out of the car. Well, what's ahead? Spreadsheets today are routinely used by accountants, word processors by secretaries. I would argue optimization should be used by engineers. The first time I ever gave a keynote address was 1978, and I confidently said that by 1985, engineers will all be using optimization. I don't say that anymore, except I can say that our client base is pretty wide and sophisticated today, and it's beginning to spread today very rapidly. And today you can learn to use optimization with a fraction of the effort that was required 4 decades ago. So with that, I'd like to thank you for attending. This is a Corvette. One of our clients, Pratt & Whitney Miller, uses Genesis routinely. They designed this wing along with a whole lot of other parts. So with that, I'd be happy to answer any questions.
Thanks, Gary. Thanks for the interesting talk. And if you guys have any questions, please type them in the Q&A panel, and we'll try to go over them. While we're waiting for some questions, I do want to let you guys know that we do provide 30-day evaluations for any of our software, be it VisualDoc or Genesis. And you just need to go to VR&D.com, and there's an evaluation link on the website. Also, if you would like to look at the webinar again, we will provide a recording in about a week's time. We will send out an email. The other thing I want to add there is about an hour and a half before the webinar, I did update the event with the actual PDF that Gary presented today. So if you are interested in it, you could download it using that email. So going to some questions. One question, Gary, is one person wants to know how hard it is to start using any of our tools, specifically without any knowledge of the optimization theory.
Yeah, I think the one chart I showed is pretty accurate, that if you're computer literate, you can use VisualDoc in a day or two and become pretty proficient in a week. Genesis is a little bit longer, but again, it's very simple. If you're, for example, if you're a Nastran user, our data is compatible with Nastran, and you can go to Design Studio and learn to use Genesis acceptably in a matter of days at worst. Fanny gives one-day seminars that have people up and running directly. I think in general, the cost of learning and the effort to learn to use this software is quite minimal, and you can be a pretty effective user very quickly. I might say again, thank you all for attending. I know some of you are up very late at night. We have attendees from all over the world, I see.
Yeah. Just to add one more point on top of that question, that answer. With every software, of course, we do, like I said earlier, we do provide 30-day evaluations for you to look into it, and the evaluation license is pretty much available with all the features of the code. With the software, we do have step-by-step instructions and also some videos on how to actually go through working with the software. So that would help get up to speed faster.
Yes, the documentation and tutorials are quite extensive.
Mm-hmm.
Go ahead, Fanny.
Another question. Yeah, another question. Is it possible to run nonlinear topology in Genesis, and what kind of manufacturing constraints are there in Genesis for the topology?
That's best answered by you, Fanny.
Okay. To answer that question, Genesis by itself is a strictly linear code. So any type of linear analysis, be it statics, normal modes, dynamics, anything, could be solved with topology in Genesis. And it's not just limited to just topology. You can combine topology with any other type of optimizations that Gary mentioned. But just Genesis itself, it is a linear code. That being said, if you want to solve nonlinear topology optimization, we do have an interface with two nonlinear codes out in the market. One is ANSYS, where we have an interface that lets you run Genesis along with the ANSYS solver for nonlinear analysis. And the other one is with LS-DYNA. So you should be able to do topology optimization coupled with a nonlinear LS-DYNA analysis. The type of manufacturing constraints that are there, the list is pretty extensive. In total, there are about 18 different families of manufacturing constraints. They include castings, mirror symmetries, extrusions, radial extrusions, radial castings, cyclic symmetries, etc. The complete list is up in the documentation, but like I said, there are about 20 different families of fabrication constraints that you can enforce on a given design. There is another question, Gary, which says, once the optimization is done, can you get the geometry as a CAD model, specifically as STL files?
Again, I think that's best answered by you.
You want me to answer it? Okay. Once this optimization is done, essentially with Design Studio, you should be able to export out an STL file with with the facets or with the final result, which could be taken into CAD.
No way to turn on sound for you. In case you haven't figured out, Fanny is an expert on all of our software, and he teaches a lot of the courses and gives a lot of webinars. So he can answer any question on the details.
Okay, this is one that you can answer, Gary. What is the difference between topology and structural optimization?
Between topography?
No, topology and structural optimization.
Oh, okay. Topology, if you imagine that first picture I have where you have supports and a load, and you'd like to know what structure to put there, you can begin by just putting a flat sheet between the two supports with the load and tell it that you want the stiffest structure you can get, but only use 20% of the material. Topology will cut out holes, if you will, in the structure and eliminate all the unnecessary parts, but leave you with the stiffest possible structure. An example of that is a cantilevered beam, and it was actually published by a guy named Mitchell in 1904. He did an analytic optimization. Where structure, now the thing in general, in topology, you find the stiffest structure. You may not find the strongest structure. So topology, most of the time, is a first step. And then given that basic structure, you can now go to both sizing and shape or combinations of sizing and shape and optimize the structure subject to all of your other constraints, stress, deflection, dynamic response, whatever. And so topology is a very good first step if you have no other idea what the structure should look like. But then from there, you can go to refine it with the general structural optimization.
Okay, thank you. One more question. Why is topology optimization with heat transfer or temperature not being so used? Why is it not used that much? Any opinion?
I don't know. I think we can have thermal loads, right? In Genesis.
Actually, yes, you can have thermal loads, and like you, I'm not sure why it is not used as much, but I would like to add that starting with Genesis 16, which is the next version, we should be able to design topology with a heat transfer load case. So you can use temperature as an objective that's coming from the heat transfer and minimize that temperature.
I might say also, if the person asking the question, if you can send us, Fanny, an email saying what your particular application would be, that would be very helpful for us as we develop the software.
Yeah. All right. We are already 5 minutes over the schedule. Once again, I would like to thank you, Gary, for taking the time, and all of you who attended all over the world. Some places it's very late in the night. I would like to thank you guys for your interest, and we'll talk again in about 2 weeks, or I should say 2 months. Mostly that's when we will have our next webinar, so please look out for the email. All right, thank you.
Thank you all.
Thanks, Gary.